So what we want to remember is that the Lewis dot diagram explains the connectivity, how the atoms are connected, single and double bonds, how the electrons are distributed to create that. The VSEPR is strictly based on repulsion. It's not a theory or anything like that. It's just basically, if you put this many repulsive things around a central atom, what type of structure are they going to make? It doesn't really tell us anything about what bonding actually is yet. So this is where valence bond theory comes in. So valence bond theory is going to be our first stab at explaining exactly what a covalent bond actually is. So here we have, basically the general idea here is that with valence bond theory, you're going to have the overlap of half-filled atomic orbitals. So two atomic orbitals each have one electron in them overlapping, and that overlapping region then would have a higher electron density, which would then result in bonding between the two nuclei. So you can see the overlapping region here for the H2, and then examples for the HCl here, and two chlorine atoms here. That direct overlap is actually given a special name. That direct overlap between the nuclei is called a sigma bond. Right. And there will be another type of bond that we'll talk about, but this one is the sigma bond. So what's exactly happening when these nuclei or these atoms come together? Well, as you can see in the picture here, as the two hydrogen atoms come, if they're out at some distance apart, they're at what we would call maybe a baseline zero energy. As they start to come together and overlap, the energy of the two atoms, that system of two atoms, the energy is going to decrease. And obviously nature likes to decrease energy, so it's going to kind of continue to decrease. So as those nuclei keep coming together, we get to a minimum energy here. Now, if we start to put these two atoms even closer together, you can imagine that the nuclei, which are positively charged, are going to start to push against each other. There's going to be electron-electron repulsion, and that stability of overlapping the orbitals starts to be outweighed by the repulsive forces between the electrostatics that are going on there. So let's take a look at a few more examples. Here's BeF2, which is a known covalent substance. Now we're going to run into a slight problem here with this one. If I look at the beryllium, beryllium's valence shell, which are the ones that are going to be involved in bonding here, is a 2s, and that orbital has 2 electrons. And I can draw the other 2 p's here, but those don't have any electrons in them. So the beryllium currently doesn't have any half-filled orbitals. The fluorine would have the configuration of s2p5, so there'd be one of the p orbitals in the fluorine that's half-filled, that we could overlap with. But the beryllium doesn't have that. Well, the answer to that is basically to hybridize this. This is the hybridization of these atomic orbitals. What do we have to mix together? So basically, hybridization is the mixing of orbitals. So if we think about it, for the beryllium, we have this s orbital, and then we have these 3 p orbitals that we could, in theory, mix together or hybridize, combine together these. All right, so let me go back over to here now. And I'll draw these new orbitals in red. But basically what's going to happen is we're going to promote this electron up. So we're going to add some energy to make that go up there. And then we're going to bring these orbitals down to the same level. So I'm going to create, in this case, 2 hybrid sp orbitals. And then we still have 2p orbitals that are unhybridized. Right, so those are two of the 2p orbitals that are unhybridized. And then the hybridized, those red orbitals, are sp hybrid orbitals. Now, we spread the electrons out, and again, if they're at the same energy level, then they're degenerate. So now we have in the beryllium two half-filled orbitals that can overlap with the fluorine's p orbitals that have one electron in them. So let's go down and take a look and see what this looks like. So here we have the hybridized orbitals. So you can see it's a blending of the s's and the p's. So we have our s orbital here and our p orbitals. Through the hybridization process, we're going to create two new orbitals. Right? Notice these slight smaller lobes here. We'll get into talking about those a little bit later, but those are going to be important at another time. But it's that larger part of the lobe. So once we combine these together, it's that larger part that's going to be available for bonding or overlapping with another atom. And so we go down further, and sure enough, we have that overlap between the beryllium hybridized sp orbitals and the unhybridized 2p orbitals in each of the fluorines. So let's take a minute to kind of rationalize that. And then you'll be able to see that directionally we would end up with a linear molecule here. Obviously those two hybridized orbitals are going to be on opposite sides from each other where the fluorines would bond to. So this would make a linear molecule. Similarly, if we take BH3, boron has two electrons in the 2s, one electron in the 2p's, and so if we promote that one electron up here and we hybridize the 1s and the 2p's, we're going to end up with three hybrid orbitals. And we would call those three hybrid orbitals then sp2 hybrid orbitals. And then, if we think again, those three orbitals that are going to try and get as far away from each other as possible would occupy the vertices of a regular triangle. And so we would end up with that trigonal planar shape, similar to what we did with the VSEPR when we had three electron domains around the central atom. And if this were hydrogen is bonded to, we could put a bond a hydrogen atom to each one of those, that half-filled 1s orbital on the hydrogen, and we get a trigonal planar molecule. Here we have the hybridization of the s and all three p orbitals. So the px, the py, and the pz. And so this would be something if we needed to bond four things together. So this would be particularly important if we looked at, for instance, methane. Oops. So if you remember for carbon, is going to be a 2s2, 2p2. So we would promote one electron up to the p's there. We hybridize, as in the picture here. So we create these four hybrid orbitals now, and that leaves then half-filled orbitals that these hydrogens, the 1s orbitals on the hydrogens, can overlap with. Right? Notice that again, with four of these hybrid orbitals all grouped around that central atom, they're going to align themselves in a tetrahedral shape. This is the same way, it's the same structure that we would get from the VSEPR model that we've used. So what happens with water? Well, if we look at the oxygen here, this is the oxygen. Oxygen 2s, 2p, and so we can look at this and say, oh, well, look, hydrogen's in pretty good shape here because we have these two p orbitals that are half filled that the hydrogen can overlap with. So if I put my hydrogen orbitals in here, so there's the 1s on one hydrogen, 1s on a second hydrogen, and then I'll show the overlap by kind of circling these. And so everything should be kind of hunky-dory. However, if we draw these orbitals, so I'm going to do the one of the p orbitals for the oxygen there. I'm going to do another one here. So these two are both in the plane of the board, right? And then the p orbital that's filled, I'm going to pretend that that's coming straight out of the board, straight at you. Right? So we would have one electron in the orbital that's running vertically, and one electron that's in the orbital running horizontally. So if we bring that hydrogen in, we'll put one hydrogen there and one hydrogen there for that overlap. Now, here's the problem. If we look at that, the angle, the bond angle between the two hydrogens here, given the structure, is going to be 90 degrees. Right? Well, we know that water doesn't exist with a 90-degree bond angle between the two hydrogens. Water exists with a bond angle that's much larger than that. So even though there's the possibility of overlapping with those p orbitals there is an adjustment so that the water, or the oxygen in the water, is going to hybridize. And the hybridization that's going to make sense with the data that we have would be an sp3 hybridization. So we're going to take the s orbital and all three p orbitals and hybridize those. And again, the shape that we get there, this one here, only what's different here is that two of the hybridized orbitals are now home to the lone pairs that are around the oxygen, and then the half-filled orbitals are overlapping with the 1s orbitals on the hydrogen. And then that's okay. So we end up with this then produces that bent shape that we're used to with a bond angle that's much greater than 90 but a little bit less than 109.5. Now, so what happens when we go beyond 4 electron domains in the central atom, or more than 4 bonds on the central atom? Well, obviously we're going to have to bring into play some other orbitals to hybridize with. So here we have our expanded octets. Right, and you can see from here, perhaps you can't see, to make 5, we're going to use the s orbital, the 3 p orbitals, and then we'll bring in a d orbital as well. And so that sp3d hybridization is going to create our familiar trigonal bipyramidal structure. And 6 are s, our 3 p's, and this time 2 d's will get involved in the hybridization. And this time we'll end up with our familiar octahedral structure. Right. So in the next lesson we'll take a look at how we form double bonds using the valence bond theory.